Okay, let's see a question that sort of plays around with different distributions. Suppose the weights of people are normally distributed. Okay, so here let x be the weight of a random person. It is normally distributed with a mean of 75 and a standard deviation of 10. Fine. Then if we ask, what is the probability of the mean, so the average of 25 people, x is the weight of one random person. So it's not this distribution here. It's not normal with this and this. Here, when you're talking about the average, we will use the central limit theorem. Okay, so here x bar, or the mean weight, will be normally distributed with mean mu and standard deviation sigma over root n. Or in other words, when we're looking for the probability that the average of 25 people is between 73 and 78, here we're going to convert these into z-scores using our central limit theorem. So x bar subtract mu divided by sigma over root n. Okay, so here I can convert 73 into a z-score and 78 also into a z-score. The key here is that in part A I'm talking about the mean weight of 25 people. So I'm going to use the central limit theorem. I'll use my z-table to look up the cumulative areas of these two z-scores, and to find the area in between, just subtract the two areas, giving me 77%. Okay, what is the probability that between 5 and 7 inclusive people, of the 25 people chosen in A, will have a weight more than 80 kilograms? I am not talking about here the mean any longer. And I'm not talking about the sum. I will not be using the central limit theorem here. Instead, I have to do this in two steps. One, I'm going to find the probability of weighing more than 80K. This is dependent on just what one person weighs. Okay, so a random person is normally distributed. That's x. So here the probability of weighing more than 80K is also normal distributed like A is. But A, I'm using the central limit theorem, which is sigma over root n. But for B, I'm just using normal, which is here. Okay, I'm not talking about the collection. I'm just talking about one person. Okay, so one person weighing over 80 kilograms, you can find the z-score. Use the cumulative z-table to find this area. Then, of course, adjust 1 minus to find this tail. So the probability of one randomly selected person weighing over 80K is about 31%. Step 2 now, we need to talk about a total of 25 people and the probability of between 7 and 5 being over 80K. This is actually a binomial situation. So let y be the number of bags which are over 70K kilograms. We found the probability of just 1. Now we're going to repeat this process 25 times, and the probability of success of being over 80K is 0.308, just like I've calculated from step 1. So then I'm going to find the probability of this in between 5 and 7 inclusive, including these points. I'll have to use the binomial PDF here 3 times, once for 5, once for 6, and once for 7. I'll add them all up, and I get the probability of B is then about 40%. Okay, C says somewhere in the city 16 people enter an elevator. Assume these 16 can constitute a random sample. What is the probability that the total weight? So here, again, total weight, or when you're talking about the mean weight, this is the collection of data that you can use a central limit theorem for. Okay, so here the total weight of 16 people exceeds the elevator's weight, which is 1,260 Ks. Okay, so here I am going to use the central limit theorem again. Again, if the total of 16 people is 1,260 or more, then the average for each and every individual person must be 78.75 or more. Again, I am now using the central limit theorem again, like I did in part 1. And here is the mean, and the standard deviation is sigma divided by root n. So here I can transform this 78.75, which is the average of 6 people, here dividing this equally. I'll find a z-score of 1.5. Look it up in the cumulative table. Here I want the tail area, so I need to make sure that I'm using the right area. And here then I find the probability that the sum of 6 people in an elevator exceeding the weight limit is about 7% chance that that happens.